Today we define positive operators, prove their main equivalent conditions, and build their square root. The idea is simple. Positive operators are the operator version of non-negative numbers. The execution is less innocent, because linear algebra enjoys paperwork. Let V be a finite-dimensional inner product space over R or C. A positive operator is self-adjoint, and its quadratic form is always non-negative. Many people say positive semi-definite. Same meaning, better name, but apparently too much honesty was available. The theorem mirrors basic facts about non-negative numbers. The theorem says these number facts survive after replacing conjugation by adjoint and squares by operator squares. Here is the central theorem for positive operators. We prove the cycle. A implies B, B implies C, C implies D, D implies E, and E implies A, because apparently one implication would be too merciful. First assume T is positive. Take an eigenvector. Positivity gives the displayed non-negative inner product. Since the inner product is linear in the first slot, this becomes lambda times the norm squared. The norm squared is positive, so lambda is non-negative. Also T is self-adjoint by definition. That proves B. Now assume T is self-adjoint and all its eigenvalues are non-negative. The spectral theorem gives an orthonormal eigenbasis with non-negative eigenvalues. Define R by taking the ordinary square root of each eigenvalue. Yes, this is the rare moment where the notation does exactly what it looks like. Squaring R sends every basis vector exactly where T sends it, so R squared equals T. We also need R itself to be positive. In the orthonormal basis, R has a real diagonal matrix with non-negative diagonal entries. A real diagonal matrix is self-adjoint, so R equals R star. And if X is expanded in that basis, the quadratic form is a sum of non-negative terms, therefore R is positive. The rest of the equivalence chain is short, mercifully. If the square root is positive, then it is self-adjoint. If it is self-adjoint and squares to T, then T equals R star R. Finally, if T equals S star S, then T is self-adjoint, and its quadratic form is a norm squared, so T is positive. Now let us isolate the square root idea. A square root of T is any operator whose square is T. A positive square root must also be positive. There can be many square roots, because operators enjoy chaos. But there is exactly one positive square root. Let T be positive. We prove that its positive square root is unique. Because T is positive, it is self-adjoint. The spectral theorem decomposes V into eigenspaces of T. Suppose R is any positive square root of T. We will show R is forced on every eigenspace. First, R commutes with T because T is R squared. So if a vector starts inside one eigenspace of T, applying R keeps it inside that same eigenspace. No escape tunnel today. Now restrict R to one eigenspace. On that eigenspace, R is positive and its square is lambda j times the identity. Every eigenvalue alpha of this restricted operator is non-negative, and alpha squared equals lambda j. Thus alpha must be the non-negative square root. Therefore R acts as multiplication by square root lambda j on the whole eigenspace. Since V is the direct sum of those eigenspaces, this determines R everywhere. There is no freedom left. The positive square root is unique, so the notation square root of t is justified. Here is the whole story in one diagonal example. The positive square root just takes square roots of non-negative eigenvalues. And this is why t star t is always positive. It is literally s star s with s equal to t. Positive operators are the operator version of non-negative numbers. The moral is simple. Positivity, non-negative eigenvalues, s star s, and the unique positive square root are all the same structure wearing different outfits. Linear algebra calls this elegance. We call it paperwork with taste.